Hi everyone, this video is going to talk about titrations. Titrations are a very common technique used in chemistry. We use titrations to determine things about solutions, maybe the concentration of a reagent in a particular solution, or you can also use titrations to determine things about a solid, maybe, for example, the molar mass of a particular solid or the percent composition of a particular chemical species. So because titrations are extremely common in chemistry, it's important that we understand them completely. So let's talk about what titrations are in the first place. What you have in a titration is you have a reaction that occurs in aqueous solution. So you have an aqueous solution of one reagent, and then separately you have an aqueous solution of a second reagent. And what you do is you add one of the reagents to the other very carefully until the reaction reaches completion. So for example, here we have a solution of A in the burette, and in the flask we have a solution of B. What we're going to do is we're going to add A into B until this reaction has reached completion. Okay, so when we do these titrations, there are a few criteria that you want for the reaction that's involved in order to have a successful titration. First of all, since these reagents are in solution, you want to make sure that your reaction actually can be carried out in aqueous solution. It's very hard to fill your burette with a solid and try and titrate a solution. So the reagents need to be able to dissolve in solution and create stable solutions. You don't want them decomposing over time because of their contact with the solvent. The other thing that you want to have for a titration is you want the reaction to occur quite quickly. Titrations are already a bit of a lengthy process, so you don't want to wait around for the reaction to complete as well. You want them to be very quick, like an acid-base reaction. You also want the reaction to be very much in the forward direction, so the reaction in fact goes to completion. It's not a reversible reaction. Now, the last thing that we need for titration is we need to know when this reaction is actually finished. You need some sort of visual indication that the reaction has been completed. This visual indication we refer to as the endpoint. Okay, so what we're going to do now is we'll talk about a few different ways that you might determine the endpoint for a particular titration. A very common type of titration is a titration between an acid and a base. Once again, the reason why this is a very common case is that acids and bases can be easily dissolved in water, and they're very quick, and the reaction generally goes to completion. But there's another very good thing about these acid-base reactions is that in order to determine the endpoint of the reaction, we often use an indicator, which are readily available and have a wide variety of colors and indicate a wide variety of different pHs. For example, let's take the case of phenolphthalein. Phenolphthalein is a very common indicator. It's a common indicator, but as we can see here, it is also pretty hard to spell. So really quickly, how about I cover up the mistakes I've made? It happens. Phenolphthalein, tough to say, very valuable indicator. Phenolphthalein, as you know, when it's in an acid solution, it has a colorless appearance, but when it's in a basic solution, it has a very bright pink color to it, very distinctive. So here's where it's very useful for a acid-base titration. So let's say that you have an acid in your flask here with just a few drops of phenolphthalein. These indicators tend to be quite powerful. You only need 1 or 2 drops in order to work for the titration. So you have your acid with your phenolphthalein. This should be what color? Well, this should be colorless. And then what we're going to do is we're going to put our base into the burette, and we'll slowly add the base into the acid until our reaction is complete. So the acid and the base have completely neutralized, giving us a neutral salt and water. Now, what that's going to do when this is neutralized is you're going to have, presumably, depending on what type of acid and base you use, you're going to have a neutral solution. So how's that going to affect the color of phenolphthalein? Well, it won't affect it very much. It may, in fact, still remain colorless once all of the acid and the base has been neutralized. But here's where it gets interesting. With that first teeny tiny fraction of a drop that's being added to the acid that is in excess, what it's going to do is it's going to turn our entire solution strongly basic. And that will be shown visually by this solution turning this bright pink color. All right, so the solution, in fact, by the time we're done, will be basic, but the amount of volume required in order to complete the reaction will be very accurately measured. If anything, the base will have been added in excess by maybe half a drop, which is in fact quite good. In the previous example of an acid-base titration, we used a pH indicator that would change color when our solution reached a particular pH. And this was what we used to visually determine the endpoint of the reaction. But sometimes you don't necessarily need a pH indicator. For example, if you have a colored chemical species in solution, that can act as its own visual indicator. So let's take an example here where I have substance A that's been dissolved in solution, and substance A, when it's dissolved in solution, produces a green solution. Substance B has been dissolved in a solution in the Erlenmeyer flask, and we'll say that this has a colorless appearance when it's in solution. Now, A and B can react together quickly and to completion as what we want for titration reactions to produce substance C, which is also colorless. So let's map out what happens when we do this titration. So we're going to be adding A, which is our green solution, into B. Now, as A reacts with B, what ends up happening is it gets converted into C. And remember, C is also colorless. So essentially, if A is being consumed by B, this solution here will maintain its colorless appearance. But let's say we get to the point in the titration where all of the B has been consumed. Well, what happens now if we continue to add a little bit more A, just a drop or two? Well, remember, since A is colored and now it's not being consumed anymore, what we're going to see is the solution is going to turn green in color. And that is what we can use for the visual indication that this reaction has reached completion. These are just a few ways that you can determine the endpoint of a reaction. There are other ways that you can do it as well. For example, maybe you might want to be just as direct as putting a pH probe into your solution and monitoring the pH of your solution. This can determine the endpoint of a particular titration. Sometimes you could even just look for a precipitate or something similar to that to determine the endpoint of your titration. There are many, many, many ways, but these are just two examples to get us started with our thinking. All right, now that we know that titrations are a reaction between aqueous solutions carried out to its exact completion, and we know a thing or two about how to determine when completion occurs, in other words, finding the endpoint of these reactions, let's go back and think again what the purpose of these titrations are. Generally, it's to find something out about the solution that's kept in this flask here. Maybe, for example, we want to know how many moles of B are in this particular solution. So what we're doing in a case like this is we're measuring how much A is required to be added to B in order for this reaction to be complete. But what do we measure with a burette? What measurement do we actually take from a burette? Well, what that would be is that would be the volume of A that we use, the volume of solution A that we use in order to completely react with the moles of B in this flask. So what does that mean? How would this help me? Well, if I know the volume of A that was required to complete this reaction, and I know the concentration of this solution of A, well, what that tells me is the moles of A that were required to consume all of my moles of B. Now, in this particular example here, A and B react with each other in a 1-to-1 molar ratio. So the moles of A that I use is equivalent to the moles of B that I've consumed. So this will tell me how many moles of B are in my solution. But what did I really need in order to make this conclusion and determine the number of moles of B that are in my solution? Well, the thing that I needed to know before I started was the concentration of A, the concentration of the solution in my burette. By the way, what do we call the solution in the burette? The titrant, that's right. When we accurately know the concentration of a solution, we say that solution has been standardized. So a lot of the processes that we do when we're doing titrations is we are standardizing solutions, determining the concentration of a particular solution in our titration with a great degree of accuracy. And this will allow us to use that standardized solution to determine unknown values. For example, the moles of B in this flask, or maybe I could determine the purity of the solid B that was dissolved in my solution in order to make this particular solution of B. Once you have a standardized solution, you can use it for many applications in determining things about unknowns. Now that we understand the importance of having a standardized solution in a titration, let's talk about some ways that we could make standardized solutions. One way is to carefully prepare a solution with a known concentration, starting with a primary standard. So I guess we need to define what a primary standard is. A primary standard is a substance where you know everything about it, and the composition of the substance, the nature of that substance, remains constant over a long period of time. So for example, a primary standard could be a solid, and what we would need to know about that solid is what it is, first of all, what the chemical species is, and its purity. We would need to know its purity to a high degree. So for example, maybe we understand that this solid is completely 100% made of the substance that we expect it to be. Therefore, if we accurately mass the solid, we should be able to use the substance's molar mass to figure out exactly how many moles are present. And, even the primary standard doesn't need to be 100% pure as long as you know exactly its purity. So let's say our primary standard is 95.2% pure. Then I know that 95.2% of the mass that I weigh is the substance that I'm expecting to be the primary standard. Again, then using the molar mass for that solid, I can determine how many moles of that solid that I actually have. So what I can do once I know exactly how many moles of my primary standard I have, I could add it to a volumetric flask. Now, volumetric flasks, they're these round bottom flasks that accurately measure one volume of solution. So essentially what you do is you fill the volumetric flask up to a particular line, and that might be 500.00 milliliters or 150.0 milliliters, depending on which size of volumetric flask you use. But they're essentially used to measure one volume of solution to an accurate degree. So we would take the solid and add it to our volumetric flask. Now it's pretty hard to get a solid into a thin neck of a volumetric flask. So generally what we do is we dissolve this in a little bit of water first and then use a funnel to add the solution into the volumetric flask. So what you're going to get is you're going to get a little bit of concentrated solution on the bottom of your volumetric flask. And then what you need to do is just fill the volumetric flask up to the line with the solvent that you're using. So up to the line, meaning the bottom of the meniscus touches that line there. So now, because we used a primary standard to start with, I know exactly how many moles of substance I've put into solution. And since I'm using a volumetric flask that's quite accurate, I know to a high degree of accuracy the volume of the solution that I've created. So now all of a sudden I have a primary standard because I know how many moles were in my flask, and I know the volume of my solution that I have. So another way of standardizing a solution is to standardize a solution of an unknown concentration through titration. So let's, for example, say that we're preparing our titrant using a solid, but this solid isn't a primary standard. So what that means is that we maybe don't know its exact composition. This may be 90% pure or maybe 85% pure. That's not something that we can determine. Or maybe this solid reacts with moisture and oxygen in the air, so while you're massing it, its composition changes over time. Essentially, because this is not a primary standard, its mass won't be directly relatable to the number of moles present. So when we add our solvent and use this to make our titrant, we don't accurately know the concentration of our titrant because we don't accurately know the composition of our primary standard. So what we need to do is we need to come up with a method to figure out exactly what the concentration of this titrant is, and we can do that through titration, in which we're titrating a primary standard. So what we'll do in this case here is once we prepared our titrant with its roughly known concentration, we're going to get some primary standard and accurately mass an amount of that primary standard into this flask. So if you want to accurately mass a solid, what you're going to use is you're going to use an analytical balance. Those are generally accurate to about the 1/10,000th of a gram. So because this is a primary standard and we know its composition, we can relate its mass, which we very accurately measured, to the number of moles of primary standard that are present in this flask here, and that will be known to a high degree of accuracy. Now, as you guys know, titrations occur in aqueous solutions, so you can't just titrate a solid here. So one thing that you're going to have to do is you're going to have to add some solvent into this flask with the primary standard. So when you're finished, what you're going to have is a solution where we know the number of moles of primary standard, but we don't necessarily know its concentration because we're just adding some solvent, enough to make a solution. But that's not going to matter in the end, because what we get up to now is we'll be using our titrant of unknown concentration in order to titrate the primary standard and figure out when this reaction is finished. And what we'll do is we'll record the volume of titrant that was required in order to complete this reaction. Now we're going to record this volume quite accurately because we're using a burette, and burettes in general, well, depending on the type of burette that you have, measures to plus or minus 0.02 milliliters of volume. So this is a relatively high accuracy volume that we're measuring here. Now, the other part of this standardization through titration is we're going to need to know the reaction between the primary standard and the titrant. So in this example here, just to keep things simple, I've chosen a 1-to-1 molar ratio between the moles of primary standard being consumed and the moles of titrant being consumed. So let's figure out what we know here. We very accurately measured the moles of primary standard that were present in our flask here. And then what we did was we titrated the primary standard until the reaction was complete. So that means through stoichiometry, we should be able to figure out the moles of titrant that were consumed in this reaction. Now, the other thing that we spent our time measuring was the volume of titrant that was required for this reaction to be complete. So we have the moles of titrant required and we have the volume of titrant that was required. So what that gives us is the concentration of the titrant. And because we knew the moles of titrant to a high degree of accuracy and the volume of titrant used to a high degree of accuracy, what this means is we've now determined the concentration of our titrant to a high degree of accuracy. So we've standardized our titrant using titration with the primary standard. Now that we've learned what titrations are, and we've learned about standardized solutions, and we've learned a little bit about the calculations involving titrations, let's get down to the nitty-gritty of the technique. Now, titration is something that does take a little bit of practice to get used to, and there are some techniques that can help us for a more successful titration. I'm going to go through just a few of them. A lot of them, well, unfortunately, you're going to have to learn a few of these by trial and error. So first, let's talk about preparing your burette. Now, let's say that you're in the lab and you go and grab your burette. Now, hopefully, your colleagues before you have returned this burette cleaned. So in other words, it might have been cleaned out with a little bit of distilled water. But these are very, very long glass tubes, so they essentially take forever to dry. So this burette that you've just taken from the lab bench may have a few drops of water inside. So what are you going to do here? Are you going to add a portion of titrant to this burette? Aren't you trying to find the concentration of the titrant to a high degree of accuracy, and here you are diluting it with droplets of water? This does not seem like a particularly good idea for me. So let's see if we can solve this problem. What we do when we're faced with a situation where we don't have a dry burette, there's already a little bit of solvent in the burette, is we can rinse the burette with the solution that we're going to be using. So what you can do is you can take a small portion of your titrant and add it into the burette, and then just take that burette and roll it around so that the titrant contacts all the surface of the burette. Now, this solution here will now be contaminated by the droplets of water. So what you're going to do is just empty that out into a waste container. You can collect the waste throughout your titration and then throw it away in the appropriate receptacle at the end of the lab. Now, what you'll do, since this has been rinsed with the solution that you're using, is you're going to fill the burette up with your titrant, and it will have the concentration that you expect. It won't be diluted by any droplets of water. Now, let's talk about filling up this burette. One thing you want to do when you get a burette, or in fact any new piece of lab equipment, is take a minute and look at it. See how the measuring will be done. When you look at the burette, you see that the 0 mark is at the top and the 50 mark is at the bottom. But after the 50 mark, there's this whole portion of volume here that's unmeasured. So whenever you're doing a titration, you never ever want to let the solution fall below that 50 milliliter mark, because then you won't know how much solution fell out of the burette between the 50 milliliter mark and where you actually finished your titration, because there's no gradation on the glassware for us to determine that. So try and avoid that. I've seen quite a few titrations fail because people have forgotten that. Now, if we look at this burette here as well, look where this has been filled. Is it filled at the 0 line? No, not at all. It's just sort of been randomly filled up somewhere towards the top. How can we get away with this? Well, when we're doing titrations, what we're doing is we're measuring the difference in volume. So what you're going to do is you're going to measure the initial volume of titrant in your burette, and then this liquid level is going to fall, and you're going to measure the final volume of titrant, because what you're looking for is the change in volume, because this is the volume of titrant that's been used. Okay, and that's the value that we're after. So you don't need to spend a lot of time getting your titrant exactly onto the 0 mark. Just fill it up wherever. Just make sure you have enough titrant to complete the titration without going below the 50 milliliter mark. So the last thing I want to point out to you about how this burette was filled was I want to point out what's going on in the tip of the burette. You see that this burette has been filled properly because the tip of the burette is filled with liquid. One common mistake that people will make is that they'll start their titration with the tip of this burette completely empty, so not filled with liquid. Well, what are you going to record for your volume of titration in a case like this? Well, you'll start by recording the initial volume of titrant, and then you're going to start the titration and the liquid level is going to drop. But that first initial drop in the liquid level, is that titrant added to your solution? No, that's not what that's going to be. What that's going to be is the titrant filling the tip of the burette before it exits the solution. So you continue your titration and you find the final volume of the titration, but the change in volume of the titrant, what that represents is the liquid required to fill the tip plus the liquid required to complete the titration. You only want to have the liquid required to complete the titration, and in order for that to be the case, you need to start your titration with the tip of this burette completely filled and no air bubbles present. When you do your titration, what you want is your titrant that is leaving the burette to mix with your solution. You don't want it to go anywhere else. One thing that I see as a problem in the lab occasionally is that people will have their burette set up way higher than their flask and the solution in their flask. So what ends up happening is when you swirl this flask, occasionally you'll miss a drop. It might fall into your flask, but it falls along the walls of your flask and accumulates on the sides rather than entering your solution and mixing properly. So these end up being lost drops of titrant. In order to avoid this, what I like to do is I like to set up my burette so that it is pretty much in my flask. So what ends up happening is any drops from my burette, they go directly into my solution and the reaction occurs in the mixed solution. Even when I swirl the flask here, if there's any sort of motion, the walls of the Erlenmeyer flask bump up against the burette, but still the tip of the burette is directly above the liquid. So any drops of my titrant will end up directly in my solution, and I don't have any unaccounted for volume. Now, the last tip I'm going to give you is how to go slow in a titration. As you're approaching the end point of your titration, you want to make sure that you complete the titration within 1 or 2 drops of titrant. So at this point, you need to go really slow. Make sure that you get the reaction finished exactly and don't add extra drops. So what I find students do when they want to do a titration slowly, when they want the drops to fall out of their burette slowly, they focus on the wrong thing. They end up focusing on how they're turning the stopcock here. And, sometimes their fingers just get away from them and they end up putting a little bit much force. And what ends up happening is you have a whole bunch of titrant that falls out of your burette and into your solution, and then all of a sudden the solution changes color and you think, well, darn it, I've missed the end point. I'm off by about 5 or 6 drops and I'm going to have to start the whole thing over again. Geez, if only I could have done this a whole lot slower. So let me give you a tip on how to do these titrations carefully. What I do is I don't focus on the stopcock. What I do is I watch the drop. What you can do is you can turn the stopcock ever so gently, and you'll see that the drop that's coming out of the bottom of the burette starts to grow a little bit. Essentially what's happening is the liquid is falling so slowly out of the burette that the surface tension is holding the liquid to the tip of the burette, and it hasn't gotten heavy enough for it to drop and fall into solution. So if you can see that drop growing, you know that liquid is leaving the burette, and that liquid is just going to accumulate on the tip of the burette until finally it's heavy enough that it's going to drop and fall into your solution. Now what you can do is you can then swirl your solution and mix that drop of titrant into the solution and observe if the reaction is finished or not. And while that's happening, what you're doing is the stopcock is still open and you're starting again, waiting for another drop of titrant to grow on the end of the burette and eventually fall into solution. So if you do this right, 1 drop of solution should fall out of the burette and into your solution maybe every 10 seconds or so. That's definitely enough time for you to swirl the burette, decide if your reaction is finished or not, and then either decide to leave the stopcock open for another drop or turn it off and record the final volume on your burette. So I hope these tips will help you in your titration. Remember, the biggest thing in helping you in your titration is to remain calm, remain focused, and keep practicing. All right, good luck in the lab.